We know that at normal atmospheric pressure and room temperature, water exists as a liquid. But at greater than 100 degrees C, it exists as a gas. And below 0 degrees C, it exists as a solid. We've seen how the boiling point of a liquid depends on pressure, so changes in pressure affect the state of a material. States of materials at different temperatures and pressures are summarized in what is called a phase diagram. Let's construct a phase diagram for water. Our diagram will have pressure in atmospheres on the y-axis and temperature in degrees C on the x-axis. Note that this diagram will not be to scale. We start with what we've seen before, the plot of the vapor pressure of water versus temperature. Since boiling is defined as occurring when the vapor pressure equals the external pressure, this curve also represents the boiling point of water as a function of external pressure. At temperature-pressure combinations above and to the left of the curve, water exists as a liquid. Below and to the right of the curve, water exists as a gas. There is a similar border between liquid and the solid, which we draw as a line. It does start to curve at extremely high pressures, but we emphasize that at low pressures there's virtually no curve compared to the liquid-gas border. One more border to draw between solid and gas, which we'll draw as slightly curved. Some points of note on the plot. If we read across at 1 atmosphere, we cross the solid-liquid border at 0 degrees C. We cross the liquid-gas border at 100 degrees C. These points are what is known as the normal melting point and the normal boiling point of water. In this sense, normal simply means at normal atmospheric pressure. There is one other point of interest. That is where all three curves come together. For water, this is at 0.006 atmospheres, which is about 4 millimeters of mercury, and 0.01 degrees C. This is called the triple point. While we know that at the normal melting point at 0 degrees C, solid, ice, and liquid can both be present, and melting and freezing can both take place. At the triple point, all three phases, gas, liquid, and solid, can be present, going back and forth. In other words, at those conditions, you can have boiling ice water. So the phase diagram allows us to see what state of matter is present at unusual pressure-temperature combinations. It also allows us to predict what process may take place when we start at specific temperature-pressure conditions and then change the temperature or pressure. For example, if we start in the gas phase at a temperature above the triple point and increase the pressure, notice that we would go into the liquid phase. We would predict that the condensation process would occur. This leads us to a general rule of thumb. Upon increasing the pressure, if a phase change occurs, the material will go to a more dense phase. Liquid is more dense than gas. It's interesting to note that the liquid-gas border stops at a temperature of 374 degrees C and 218 atmospheres. So you might ask, what happens if you take water vapor at a temperature greater than 374 degrees C and increase the pressure? At pressures that high, the density of the liquid is no longer greater than the density of the gas. So there is no phase change. This point is called the critical point. At temperature-pressure combinations above the critical point, the material becomes what we call a supercritical fluid. Think of this as another phase of water that can have its own properties. Finally, let's start with the solid and increase the pressure. Notice that, due to the negative slope of the border between solid and liquid, the material goes to the liquid phase. We predict that melting would occur. Given our rule of thumb that a more dense phase is produced on increasing the pressure, we conclude that liquid water is more dense than ice. We know this to be the case since an ice cube in a glass of water will float to the top. This is a little unusual, since for most materials, the solid is the most dense phase. For most materials, the slope of the border between solid and liquid is positive rather than negative. But the slope of that border indicates the relative densities of the two.